Hello, everyone, and welcome to Talk Nerdy. Today is Monday, September 2nd, 2019, and I'm the host of the show, Cara Santa Maria. I'm actually recording this intro from South Africa from a lodge where there's very crappy Wi-Fi. So I'm going to keep it short and sweet so I can actually upload this file. Today's episode features Kit Chapman, but before we dive into that, I want to thank those of you who made Talk Nerdy possible this week. Remember, Talk Nerdy will always be 100% free to download, and that's because of the support from listeners just like you. So if you want to support the show, just visit patreon.com/talknerdy, just like these kind folks did. They include Jeffrey Sewell, Brian Holden, David J.E. Smith, the Zombie Drummer, Phil T-Bear, and yes, Dudus Infinitus. Thank you so much for your support. All right, so let's talk about this week's show. As I mentioned, it features Kit Chapman. He's a science journalist from the UK, and he has a brand new book called Superheavy, Making and Breaking the Periodic Table. So without any further ado, here he is, Kit Chapman. Well, Kit, thank you so much for joining me today.
No worries. Thanks for having me.
Of course. So we are going to talk about all things elements. Your new book is Superheavy, Making and Breaking the Periodic Table. And of course, as a science journalist, I'm wondering, maybe we can dive right in. What made you want to focus on this very, very big topic? I mean, honestly, the periodic table is the, I guess, physical or the written embodiment of like everything that exists in the universe.
It is all matter. Anything that is matter, you're part of the periodic table. The answer is that I didn't know something and I was really, really embarrassed about it. So I was driving back from work and there was a guy on the radio and someone asked him how many elements are there, and he immediately said 118. And I thought, wait a minute, there aren't. There are only 114 at the moment. At the time, that was correct. A week later, they announced 4 new elements. How does he know that? What am I missing? So I started delving into how elements are created, how they're made. And this is the naughty step of the periodic table. This is the part of the periodic table nobody seems to care about, because these elements, they exist for fractions of a second. Oganesson, the longest we've ever managed to get it, is 0.06 seconds, I think it is. So it's incredibly short-lived because it's so radioactive. It doesn't exist on Earth. And so chemists just don't really pay attention to it. And so I thought someone needs to find out the stories about this. Why are we making these elements? Why are we trying to expand the periodic table? What's the point? And just entered into this weird world of particle accelerators and very, very eccentric people.
So, I mean, obviously I'm probably getting ahead of myself here, but I have to know, why are we doing that? Is the argument really that potentially there is going to be some sort of utilization, even if we don't know what it is right now? Or is it just pure unbridled curiosity and interest?
There's a whole mix. So initially, when we got past uranium, which is the first elements that we started making, there was a very real reason. We were trying to make an atomic bomb. So plutonium was discovered in the University of California at Berkeley by a guy called Glenn Seaborg. And this was actually in 1940. Sorry, 1940 was neptunium, 1941 was plutonium. And so this is when the Second World War was raging. And America wasn't in the Second World War at that point. And in fact, he told his boss that he could make enough plutonium to make an atomic weapon. And he flew over to the committee, the uranium committee was called, part of the Manhattan Project, to make the atomic weapon, and said, Glenn Seaborg says that in 6 months he can upscale plutonium. And James Collins, who was the president of Harvard at the time, said, don't be silly. He's a very competent chemist, but he isn't that good. But lo and behold, the first atomic weapon was plutonium. Past that, we've found other uses, these elements. So plutonium obviously is great for power. Americium, we use that in smoke detectors. Curium, where you can use that to measure different things. We use it in spectroscopy up on the Mars rover. We've also used it in medicine. But past that, once you get past about Einsteinium and fermium, you really can't make them last long enough. So it is pure scientific curiosity. But what we're finding is that they stop following the rules of the periodic table. So the periodic table is organized in rows and columns. And as you follow the columns down, you expect what we call periodicity, periodic trends. So lithium, that fizzes a little when you add it in water. Sodium, it flames. Potassium, it explodes. When you get to oganesson, which is the heaviest element we've discovered, that's supposed to be a noble gas. And noble gases are famously unreactive. They're things like neon and helium. Oganesson is a highly reactive metal. It's a solid, basically. It's a semiconductor, we think. So it isn't a noble gas in any sense. And that's incredible. Weirder still for chemists, we think that it doesn't really have electron shells. It just forms into this electron. Yeah, it forms into this sort of electron soup. It's part of what we call relativistic effects. Basically, the larger the nucleus gets, the more it influences electrons around it, and it changes the properties. Now, we see that elsewhere in the periodic table. That's why gold is a golden color, mercury is a liquid. But for the super heavy elements, it means they actually stop following the periodic trends. So we've broken the periodic table. And knowing is really exciting.
So we just kind of like glued them to the end. Like, is that really not where they go, do you think?
We think that that's where they go as far as organesson goes, because we can follow the subshells and where you assign electrons. Once we get to element 119 and 120, we're pretty certain they're going to go in group 1 and group 2, which is as you would expect with the periodic table. The interesting thing is when we get to 121, because we have absolutely no idea where it's going to go. And in fact, there are multiple different periodic tables. You can sort of Google this extended periodic tables. We think the element is about 171, 172. And there are so many different ideas. We could have sort of leaps and jumps where elements should go. We could have a new series that sits under the lanthanides and the actinides, as we call them, the sort of separate ones that are at the bottom of the periodic table. Or we could have something entirely different. There are so many different ideas. No one knows how our universe is put together. And that's why we're doing this research, because it just changes our understanding of matter.
Wow. And so, okay, I'm looking at a periodic table right now.
We started off like at the big questions.
No, I know. That's what I do, man. That's how this works. I'm looking at a periodic table right now. I've like Googled one. And I don't know if anybody else is doing that. Don't do this if you're driving, people. What are you doing? But yes, if you are at home, hopefully you're looking at one. There's the row of elements that's kind of like pulled out and placed at the bottom.
Yes, we've got two bits are pulled out and placed at the bottom. There are two rows of it. One's lanthanides, and there's a big argument in chemistry at the moment as to what starts the lanthanides. But let's go with lanthanum, which makes sense. And below that, you should have actinium, and that starts a row called the actinides. And these elements are very strange because they all kind of behave very similarly to each other. What's happening is it's how their electron shells are filled. Basically, they start filling in shells first. And so they're sort of dragged out of the periodic table. Now, previously, when we first had the elements that just existed on Earth, we didn't have that actinide row at all. The lanthanides we knew that they were a bit weird. We dug them up largely in Sweden. There's a tiny village called Ytterby. It's just outside Stockholm. And I mean, it's like 5 houses and a flagpole. That is all that's in this village. And a guy was digging around there, and he found this strange black rock, which he sent off to a geologist friend, and he sent off to a chemist. And we just got a whole host of elements from it, which is why we've got so many elements that begin with yttra something or other. We've got terbium, erbium, yttrium, erbium. It's all from this one village. So below that, the actinide line was actually not where it is today. So originally, uranium was under tungsten, which is W on the periodic table. So it currently where seborgium is, that's where uranium was.
Yeah, that's kind of like halfway down. That's element 74 is tungsten.
Exactly. So element 92, uranium, was actually below that originally. And the guy Seaborg, he said, actually, hang on a minute, I think that there's this other row going on. When you see a periodic table sort of fully stretched out, the lanthanides and the actinides aren't actually at the bottom. They're sort of this thin strip that separates what we call transition metals from the earlier groups.
Oh, and then there's like a gap between, I'm going to see if I can pronounce this right, scandium and titanium, and a gap between yttrium and zirconium.
Very good. Yeah, I just realized you've got a periodic table in front of you. I was going like, that's amazing.
No, I definitely have a periodic table in front of me.
Yeah, so originally we changed our entire understanding of the periodic table pretty much immediately after the Second World War. And actually, funnily enough, Seaborgium is named after Glenn Seaborg. And he was actually the guy who said about the actinide row. So the element that is now called seborgium, and that's really controversial, by the way. That almost started the new Cold War. We can come back to that.
Oh my God. Okay.
Yeah. There's juice in this story. Originally, that's where uranium was.
Fascinating. I mean, I feel like we could literally just look at a periodic table and talk about it for 17 hours, but we're not going to do that. I mean, we are going to do that, but not for 17 hours. But because there was literally a moment, this shows you how long it's been since I took chemistry. There's literally a moment where I was like, why does my periodic table only go to 103? Like, oh, I found 104 to 118.
Yeah, it jumps around.
Yeah.
So the actinides go as far as 103, and then it jumps back to the seventh row, as we call it.
To Rutherfordium.
Rutherfordium, which again, another really controversial element. So after lawrencium, actually a little bit before that, after fermium, which is element 100, all the elements of that are so unstable that they exist for fractions of a second, seconds, minutes, maybe. They're highly radioactive. They're constantly breaking down. And what you had during the Cold War was the Americans and the Russians were claiming that they had made these elements, but they couldn't prove it because the elements didn't exist physically. And they're making them one atom at a time by shooting two lighter atoms together in a particle accelerator, smashing them in. And so the Americans would say, we've discovered this element. And the Russians go, no, you couldn't possibly have done it. We've discovered that element. And so for 40 years, we had what we called the Transfermium Wars, where both sides claimed they discovered the elements. And they would give them different names. But the thing is, the Russians discovered element 103, which the Americans claimed was lawrencium, after Ernest Lawrence, a guy who invented a type of particle accelerator called a cyclotron, very big in California. He was actually from South Dakota, but very, very famous guy, Nobel Prize winner. The Russians wanted to call it Rutherfordium, element 103. And so the Americans went, okay, we've discovered 104, and that's Rutherfordium. So you had two Rutherfordiums depending on which side of the Iron Curtain you were on.
But hey, that's kind of interesting that there was, I don't know, I often think about this, that in wartime or even in like times of kind of geopolitical conflict, maybe we could say, that there's this strange, I don't know what the right word would be, ambivalence. That's not quite the right word, but where science can often be used as a tool for conflict, but at the same time, it's one of the best kinds of diplomacy that we have.
Oh, this was absolute diplomacy. I mean, when mendelevium was named, that's element 101. Glenn Seaborg wanted to honor the Russians. It was actually a guy called Al Giorso, incredibly wacky character. He's discovered more elements than anyone else. Al Giorso was Glenn Seaborg's assistant. And he only had a bachelor's degree in electrical engineering. His father was a bootlegger. He used to do ham radios. He used to make Geiger counters just outside San Francisco, and he got roped into helping create elements. Anyway, he wanted to name it after Dmitry Mendeleev, the guy who had created the periodic table to begin with. One of the guys. We can go into that if you want as well. Very, very controversial guy. Dmitry Mendeleev, weird guy. Don't have him as your hero as well. He chased a student, an 18-year-old student, across Europe to Italy, writing her love letters saying that he'd commit suicide if she didn't marry him.
Oh, no.
Well, it gets worse because Dmitry Mendeleev, he'd just had a divorce. But in Russia, you had to wait a certain time before you could marry again. So he ended up bribing a priest to allow him to commit bigamy to marry a student.
And how old was he?
40s. I think he was in mid-40s.
Yeah, of course he was.
It's icky. There's no getting around it.
Oh, yeah, because I'm sure there was no coercion there whatsoever. I'm sure this 18-year-old girl was just totally pleased as punch. Oh, my God.
Yeah. I mean, you can shoot down so many heroes. Antoine Lavoisier is another huge hero of sort of chemist, the first chemist. He met his wife when she was 13. Well, that was normal for a French aristocrat in those days, I guess, but still a little bit creepy.
Yeah, it's one of those interesting things, right? I mean, that's a whole other conversation, but about looking at people in the context of their time, but also realizing that even in the context of the time, that's disgusting.
Yeah, it's grody. It's not nice. So Mendeleev on the periodic table, we can't get away from that. Glenn Seaborg was friends with Richard Nixon. When he first won his Nobel Prize, which was in early 1950s, Nixon was obviously governor of California. And he sort of said, we should stick together, as Nixon was wont to do. And so Glenn Seaborg said, well, actually, we've just discovered an element, and we've named it after this famous Russian. And Nixon went off to meet Khrushchev and have his sit down. I think it was the kitchen table debate or something like that it was called. Very later on, Glenn Seaborg receives an original signed Mendeleev copy of the periodic table from a Russian fan saying, thank you so much for sharing. So Nixon had actually told that story, that chemist's story, to Khrushchev while he was trying to make peace. So you're right that there is this political union, but at the same time, there's huge division because the Americans and the Soviets wanted to name the elements for political reasons. One of the elements the Russians wanted was Kurchatovian, which is after Igor Kurchatov, the discoverer, the founder of the Soviet bomb project. And the Americans absolutely hated this idea. Said, there is no way you can name an element Kurchatovian. Outrageous. Eventually, they didn't. Eventually, it got settled. But Glenn Seaborg, of course, worked on plutonium. He was the guy that made the first atomic bomb possible. And so when his name was proposed, the Russians went absolutely crazy, said, no, you can't do that. They tried to implement a rule saying that you couldn't name an element after a living person because Glenn Seaborg at the time was alive. Political sort of machinations. And we have the periodic table as it is today. But yeah, incredibly messy.
It also makes you wonder a little bit, I'm not sure. Did you see the most recent mini television series, Chernobyl?
I did a bit of it, yes.
A bit of it, yeah. So obviously it's really beautiful. Like some people had some issues with some of the science, but I think that they actually did a really incredible job trying to stay true, at least to history. It was a bit weird that everybody had a British accent. That's neither here nor there. But
it's not weird for me. That's perfectly normal.
Yeah, right. But it does make you wonder, kind of seeing a film like that and obviously it's very easy to talk about kind of, I don't even know how to put it, but this kind of Cold War Russian era cloak of doing everything for the state and blah, 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 as if it weren't at least to some extent like that in the US as well. But it makes you wonder who was making these decisions, right? Like we said, at the same time that science has been used for diplomacy across the world. And of course, I think we're often talking about the scientists fighting for conversations and open discourse and dialogue and fundamental things that they find fundamentally important, like conservation, for example, or like climate mitigation. And then on the flip side of that, when you see science used as a tool for division and destruction, I often think that the powers that be are much more kind of governmental influence powers, utilizing the science and the scientists for, whatever that agenda might be. It's probably not as clean cut as that, but
I don't think it is. I think you look at someone like Haber, for example, Fritz Haber, who famously was a fan of chemical weapons, so much so he dedicated his Nobel Prize-winning speech to how we should freely gas people and things like that. How it's a cleaner death. So there are certain, but I mean, to answer your question about what it was like, the person that was leading the group was a guy called Georgy Flerov in Russia. And Flerov got into this by writing a pen pal letter to Stalin. So he was in the Soviet Air Force. He was a nuclear physicist, but he'd been recruited because the Germans had invaded the Soviet Union. And he noticed when he was going back behind the lines and trying to relax with his science journals that no one was writing about nuclear fission at all. It was the great new discovery. No one was writing about it. And he said, someone has to be making an atomic weapon. And so he was actually a student of Kurchatov's. And he wrote to Kurchatov and said, look, we've got to start making an atomic weapon. And Kurchatov said, yeah, but Joseph Stalin, he wants to focus on metallurgy, he wants to make more cannons and things like that. So Flerov wrote to Joseph Stalin. And it's an amazing letter. I mean, he sort of really puts himself out there. I mean, Joseph Stalin, not known for taking pen pals, but he throws himself out there. And it happens that the letter arrived on Stalin's desk just as a heap of intelligence about an atomic bomb project arrived. And Joseph Stalin immediately calls in his scientists and says, one, why is this guy only a lieutenant? Let's promote him. And two, why aren't you working on an atomic bomb? So he sort of kick-started all of that. And then he later moved into element discovery. He was a strange character. He sort of wouldn't let his people do other things. He said that they were guerrillas if they went off and tried to do things behind his back. But he was very, very much a stickler. And so he probably came up with a lot of the element suggestion names. But things weren't all that stilted in the Soviet Union. So I've actually been to Dubna. It hasn't actually changed much since the 1950s when they built it. It's still very much Soviet-era buildings. The hotel I was staying at has this floor that no one can access. It's where the KGB used to listen in on the guests and all that kind of stuff. And I've heard stories of Americans who've gone over there, and they've very much been down to business in the lab. They've got KGB minders following them around. And one day, the Russian laboratory guys say, why don't we go into the woods and we'll have a chat and we'll have a sort of, a Camp David style meeting. And as soon as the KGB minders are gone, out comes this illicit radio, and they tune in to Johnny Rivers' Secret Agent Man. Secret Agent Man. And they all start jiving and dancing around. The ice breaks immediately. The Russians and the Americans realize that they're all just scientists after all. So there is that camaraderie there, but there is also that fierce competition. And to this day, American scientists won't accept the periodic table names as they are. So there's someone called Darlene Hoffman who we should definitely speak about. And Darlene Hoffman insists that element 105 is not dubnium, it is harnium, because it was discovered by the Americans, and that's the American name. So there's still a little bit of resistance.
Yeah, tell me about that. Where on the periodic table, for example? Okay, maybe we'll take a step back. Who determines what I'm seeing when I Google this? Like, is there a governing body that's international that comes to these conclusions? Because otherwise, wouldn't every country have a different version based on their political whims?
There absolutely is. It is called the International Union of Pure and Applied Chemistry. That's IUPAC. And there's also an IUPAP, that is the physics version. And they come together and they have a body that's basically a judge and adjudicators. And they have a look at the evidence that you put together and say whether or not you have created a new element. And so that's how we decide whether an element has been discovered. And there are criteria. There are different measurements you can do, proof that you can actually show that you've made an element. The original periodic table was put together basically because we knew all of these elements existed. If we go back to Lavoisier, right at the start, he was the guy that first made a list of elements, but he could only do that because of his wife. She spoke English, and so she was able to translate English for him because he only spoke French. But shortly before having his head lopped off in the Revolution, the French Revolution, he put together this list of elements, and he decided that was the most basic compounds that existed. You couldn't break it down any further, and he included things like light and calories, which eventually got rid of. Then 1869, we get Dmitry Mendeleev, and he's the guy that actually thinks, all right, let's try and put these in order of weight. And when you put it in order of weight and start listing them down, you start seeing these sort of patterns emerge. And he predicted that certain elements would be discovered and they would have these properties. So I know this element is going to be underneath this place in the periodic table, therefore it must act the same. So to give you an example, we spoke about lithium earlier. If we didn't know sodium existed, I could say, okay, I've got an element that fizzes in water. I suspect the next element will burst into flames in water. And so you can put sodium there. So we started constructing this periodic table. Around the First World War, a guy called Moseley, he was working in Oxford, and he made the breakthrough, really. And he worked out it was something to do with actually what's going on in the nucleus. Say that nucleuses didn't exist at the time. It's all kind of anyway. He made the breakthrough about atomic charge, and what it is protons. So in the nucleus, which is the heart of the atom. If you imagine an atom, that's what everything is made up of. Imagine that's the size of a cathedral. The nucleus is a fly in that cathedral. It's absolutely tiny, but that is basically the most important part of an atom, because there you've got the neutrons and you've got protons. And the number of protons you have in the nucleus determines what element you have. So 1 proton is hydrogen, 2 protons is helium, 3 protons lithium, beryllium, and you can go on up and up and up and up until you get to oganesson, which has 118 protons.
So how did this guy know this if the proton hadn't been discovered?
Very good question. He was looking at charge, and I'm trying to remember exactly what he did with it. I can't remember because his research actually got interrupted because he actually signed up for the First World War and ended up in a place like Gallipoli in Turkey and was killed. And very shortly afterward, Rutherford, who obviously we do have an element named after, Ernest Rutherford. He discovered things. He discovered different types of radiation. He discovered the nucleus, discovered the proton, and he predicted the neutron existed because protons have positive charge. And that's a problem because if you imagine trying to have a load of positively charged magnets all in your fist, they're going to want to push apart, right? They're going to try and repel each other. So you need to have some sort of packing filler that has no charge whatsoever. And that's what the neutron is. The neutron sort of pads out the nucleus and makes sure that we can actually hold it all together through various different quantum mechanics, which I won't go into. And so he predicted this, and later on, this very, very British man called Chadwick, who was working in Cambridge, And he finally managed to prove that we had the neutron. And all this was happening in the 30s. And then, if you think about it, 7 years later, we suddenly have nuclear fission. We actually have, we think we have the first elements about 2 years after Chadwick was doing this work. It's amazing what happens so quickly because people realize what's going on.
There really are these like bottleneck discoveries, aren't there, where once you've kind of opened something up in that way, so much science can now follow, and it just happens very quickly.
Oh yeah, and the guy that really does it for the elements is a guy called Enrico Fermi. So he's working in Italy around in the 1930s, very famous physicist, working for Mussolini in a tiny villa, and he works out that he jumps into a fish pond with a neutron gun and works out that water slows down the neutrons. And it's like, fantastic, black magic, he shouted. Apparently, went around it. His mate thought he'd gone crazy. And he dragged that up and he started shooting uranium with neutrons because he thought uranium's the heaviest element we know, 92. That's the heaviest thing we've ever dug out of the earth. What happens if I shoot it with neutrons? And he got a result that he couldn't explain. It was very clearly not a lighter element. And so he assumed that it had undergone something called beta radiation, which is when the nucleus captures a neutron and a neutron turns into a proton. And if you turn into a proton, you move one place up the periodic table. So 92 protons, you add one more, you've got 93. So he made element 93.
And this was the first synthesized element?
Well, no. Because so he wins the Nobel Prize for doing this. And in fact, that's great for him because his wife's Jewish. And he actually discovers he won the Nobel Prize on Kristallnacht when that's happening in Nazi Germany. And they're able to flee Mussolini's fascist Italy. They say, don't worry, we're going to come back. We're just going to go and collect the Nobel Prize. We'll be back with you really soon. They get on the first ship to America and they escape. So fantastic news. But no, he hadn't. What he'd actually done was there was so much energy in the nucleus had just blown apart in what we call fission. It released all that energy. And that's what powers nuclear reactors. When they explode, it releases all that energy. E equals mc squared. M, the mass, it might be very, very small with an atom, but c squared, then the speed of light squared, that's a huge number. And so you break up one uranium atom, it'll shake a grain of sand. If you break up a kilogram of uranium, it will flatten a city. So he was wrong, but the principle was sound. Because while fission is more common, that's probably going to happen, 99 times out of 100. Occasionally, neutron capture does happen. And the first element that was actually found was by his sort of assistant apprentice, a guy called Emilio Segre. And Segre wrote to Berkeley and said, hey, you've been using molybdenum, element 42, in your particle accelerator. Can you send me a sample? Can you send me a used filter? I just want to have a look at it. And they ship it over. He's in Sicily at the time. And he looks and he finds that, sure enough, a neutron had gone into a molybdenum nucleus and that had become element 43, technetium. And element 43 didn't exist at the time. It was a hole in the periodic table. The first element that was actually created was technetium.
Oh, interesting. Were there any other holes like that at that point? So it's not that scientists, once they learned how to synthesize these elements or create these elements, were just adding to the end. There were actually gaps where people knew something should exist, but they'd never found it.
Exactly. There were a couple of other gaps. There was one at 61, which is promethium. I'm trying to remember the numbers. You have to bear with me if I get them wrong.
Bananas that you know this stuff off the top of your head, by the way. Even knowing that you wrote a book and did all this research, I have no idea how you could remember this much stuff off the top of your head. It's amazing.
The other one they made was astatine. So three of the elements were made. There was another gap which was at francium, but that was discovered by someone called Marguerite Perry. She was an assistant to the Curies. And she actually found the element through dogged hard work. Frankly, she didn't make it, but that filled in all the gaps. And then after that, along comes people like Seaborg, and the first guy is actually called Edwin Macmillan, and he shoots uranium, exactly the same thing that Fermi did, and he gets something, and he thinks this can't be Fermi's mistake. This has got to be something new. And so he shows it to Segre, and Segre goes, no, that is not a new element. Don't be stupid. What a ridiculous idea. He writes a paper saying a failed search for new elements. It turns out Edwin Macmillan absolutely had. He asked for a second opinion from a guy called Phil Abelson. They discovered neptunium, element 93. And Seaborg, he's a chemist. He's not involved in this at all, but he's fascinated. He actually follows Edwin Macmillan into the shower and starts going, what's happening about this new element? I'm really interested. And so he takes over the work when Macmillan goes to work on radar, and he gets plutonium. And from there, they're adding and adding and adding. And they get up to californium just by adding, basically by keeping things in a nuclear reactor. A nuclear reactor is like a radiation bouncy castle. You can sort of... It's it's the sides. You just fill it with neutrons, and you stick your uranium in, and you hope that neutrons hit it and turn it into plutonium. And you nudge up the table. They get up to californium, and then they just can't get enough neutrons because fission is far more common. So every time you go up an element, you are getting diminishing returns. You're getting smaller, and so the Americans come up with a brilliant idea to get new elements for Einsteinium and fermium, elements 99 and 100. They set off a hydrogen bomb, and they order fighter pilots to fly into it. So in 1952, Ivy Mike, the first ever hydrogen bomb, is detonated. And that creates so many neutrons just in the debris flying around. I think it's 10 to the 24 per centimeter squared. It's a massive amount of neutrons, ridiculous amount. And the US had worked out that they could order fighter pilots to fly into the mushroom cloud and just have filters on their wings and just scoop up whatever crap's there. And so they order several fighters to do it. The first flight was 4 of them. Three of them made it back. One of them actually died doing this, a guy called Jimmy Robinson. His circuits are scrambled. He runs out of fuel, and he tries to land on the water because it's the middle of the Pacific Ocean. There's nowhere to land. And tragically, his plane flips. Now, he couldn't parachute out because to protect him against radiation, they'd given him a lead-lined jacket. So Jimmy Robinson loses his life discovering these 2 elements. And these samples are pulled out by the US Air Force. People called the decon grunts, they used to be called. They whipped out the filters on big poles and shipped them back to America. And lo and behold, in America, they find traces of what turns out to be 2 new elements.
All right, guys, let's get back to the show. Jesus, was it worth it? I mean, it's interesting, obviously, for posterity looking back. This was a huge discovery. Did the guys? Is this a stupid question? Was there any fallout from this? Like, was there radiation sickness, like from flying directly through a mushroom cloud?
Well, the first guy who did it was a guy called Paul Fackler. He did it in 1940s, and he said he actually. he said he did it by accident. Whoops, sorry guys, didn't mean to do that. And he then flew through some rain clouds to wash down his bomber. It was, and he said, no one killed over, no one got sick, no one died. It's fine. And they actually continued doing this until 1962. Americans, until testing ended. They used to order. They actually had a special sort of squadron for flying into mushroom clouds. And obviously, today, I think that there is certain evidence that some people certainly did get sick, but Robinson's story is the worst because it actually took 50 years before he got a headstone. It was only until 2002 that he had a headstone at Arlington. He fell into sort of a bureaucratic black hole because it's atomic bomb work. So who looks after this kind of thing? And so he 2002 until his widow got a flag. His daughter, I've been speaking to her and obviously telling her because she didn't know. She knew the mission that her father died on. She knew how he died and she knew the story, but she didn't know that the elements had been discovered from that. So for that concept, and her daughter is actually a chemist, which is fantastic, sort of to be able to see full circle. But yeah, it's a horrific story. In terms of whether it's worth it, beyond that, those are the only 2 elements we've discovered using nuclear weapons. Beyond that, we actually smashed them together in a particle accelerator, and it's just adding numbers. So if you want to make organesson 118, you take californium, which is 98, you smash it with calcium, which is 20, and you make 118. It's a bit more complicated than that because that is quite difficult. You used up a lot of energy and things like that. Which we can go into again if you want.
Have we found uses for them yet? Like, is every element that we've kind of created, have a functional, I mean, not that, and that's such an anthropocentric kind of thing to say too, like, have we figured out how to use it to our advantage? Then again, we are creating it. So
The answer is no. We haven't. So some of them are so short-lived that one thing to remember is it's really expensive to make these things. So you have to use a special type of calcium that's got extra neutrons, because when you smash them together, you've got so much energy, it's far likely they're just going to burst, right? They're going to explode. So you lose the energy. And what you do is you throw a neutron out like ballast, like from a sinking ship, just try and release that energy. And so we use a very rich type of calcium called calcium-48, which is incredibly expensive. And we're using absolute grams of this stuff, and we're shooting a beam, we're getting maybe one atom a week when we're shooting a beam. So you're using it 24/7, 7 days a week, you're getting one atom. Incredibly expensive. And we're shooting 6 trillion ions a second at our target. It's very, very hard to make these things, and because they're so short-lived, it's very hard to do experiments on them. We can do experiments on some of them. The heaviest we've done is fluorovium, which is 114. And basically, we just sent it down a temperature gradient and saw where it stuck, because that is all you can do in sort of 2 seconds, which is what you've got.
is this the kind of thing, though, where people who are listening, who, maybe they're science enthusiasts, they're science interested, but they also care about, where our federal funding goes, and they understand, that it's complicated, right? And sometimes things come downstream from our science that we don't even expect. Sometimes they simply don't. I mean, is this the kind of thing where there have been arguments before Congress for like, why are we spending so much money on this?
Absolutely. I mean, that goes right back to the 1970s as well, because Gyorso, who I mentioned, he was the team leader at the time. He used to get really mad because all his funding went to the Vietnam War. So, there is a limited pot. And that's part of the reason that only so many labs are doing it. So there's one in Russia, there's one in Japan, one in Germany, one in America that's working with the Russians, and there's another one in America that sort of looks at a little bit lighter elements. And you're absolutely right. The question is, why is this funding going there? I actually asked one of the people there, one of the team leaders, and they went, well, that's a fair enough question, because if I had to pick between this and renewable energy, obviously renewable energy right now is more important. Climate change is more important than this. But understanding and being able to unlock the mysteries of the universe is what drives us. We need that sense of discovery. We need to be pushing boundaries. We always need to be doing that. It's part of human nature. And so, these things are incredibly rare. They are chemistry's unicorns, if you like. But it's part of our nature as humans to try and find the answers to questions we don't know. And I think that's why we do it.
At a certain point, however, does it become, I don't know, is it answering questions that we don't know if we get to the point where we're just adding and adding and adding? Or does it make just as much sense to have these boxes of theoretical elements, even though we've never actually seen them for that, fraction of a second?
There is that argument. I mean, one thing that you can look at is what's going on in neutron stars. So these elements do exist in neutron star collisions. And we need to be able to understand that. And we need to be able, because we get all kinds of benefits from that kind of research. At the moment, when we're trying to model something like a supernova, even the world's fastest computer in the world, that's Summit at the moment in Oak Ridge in Tennessee, that can only manage to calculate it as far as, I think, as iron. It can't go any beyond that in terms of elements being created, because there's just too variables going on. And this is something that works at, I think it's 170 petaflops a second. It's an astonishingly fast computer. You think about Commander Data boasting that he could do sort of 6 petaflops or something like that. No, 6 teraflops. So it's about 1 billion trillion times faster than Commander Data, whatever.
Yeah, that's a meaningless number to most people, I think. It's just, this is like so big.
I'll tell you one that's meaningful to people. When I went into its predecessor, which is about 100 times slower, I think it was called Titan. That's the size of 4 basketball courts. It's made up of 19,000 NVIDIA graphics cards. So imagine running Crysis 19,000 times simultaneously on the same computer.
That's amazing. That's the old one. Yeah. Science is so badass. I mean, and it you keep coming back to this question of like, I don't know, it's sort of the question that stands out to me is there an end to this? Meaning, like, at a certain point, will we be unable, like, is there a theoretical element number that we can't go beyond, where it doesn't even exist in the universe. It wouldn't exist in the furnace of a star.
We think so. We think it's about 172. But this changes. I mean, when we were in the 1940s, we thought it was about 100. In fact, they were talking about, when they created the first elements, to call it something like ultimum or something like that at the end of the periodic table.
Yeah, not a good idea.
Not a good idea.
If I know anything about science, is that there's nothing finite about it.
Exactly. Richard Feynman, a very famous physicist, he said that it would be 137. As I say, we currently think it's about 172. So there's about a third of the chemical universe that we haven't discovered yet.
Holy shit! Seriously?
Yeah, it's crazy. And the thing is, when we get to those relativistic effects we were talking about right at the start, these elements aren't going to be elements that in the way that we think of them. We think there's going to be an area where they won't be able to attract electrons. They will just be cations, what we call them. No electrons for an element. And that for a chemist is weird, because that means there's no chemistry. There is an element that cannot do chemistry on. Chemistry is all about electrons. So there's some theories that say that the nucleus will be twisted into a donut shape to try and maintain a sort of a stable condition.
What?
It all gets...
That's amazing.
It gets mad.
Well, I mean, it's the same thing with our modern physics, right? Like, in order to really understand the math and make the math work in a lot of cases, we have to get into spooky stuff with quantum mechanics. Like, things start to get weird once you really change a lot of the parameters that we're used to.
Oh, yeah, absolutely. Quantum mechanics scares the life out of me. It really does.
It scares the life out of most quantum physicists, too. It's so funny. Every time I interview a quantum physicist, they're always like, yeah, I mean, we get it, but we don't really get it. And I'm like, oh, that makes me feel better.
When we're talking about elements, there's no way that we could have anything past hydrogen if we didn't have sort of quantum tunneling. You know, that's how we get helium. It's got to behave like a particle and a wave. I get freaked out about the silliest things, but that really bothers me.
So, I mean, we've been talking about so many fascinating stories, so many fascinating discoveries, the way that the periodic table has kind of grown and reorganized over the years. I can't fathom that you've managed to squeeze all of this into your book. I mean, how did you pick and choose how much detail to go in, how many sort of corridors to go down? There's just so much. You could probably write a 10-volume encyclopedia just on the periodic table.
So I'm addicted to human stories, and I look for the craziest stories that there are. You know, when I found out that Colonel Sanders, KFC, he worked on the Manhattan Project, I wanted to know about that.
What?
Yeah, he was the cafeteria manager at Oak Ridge. Superman, I found out that he got in trouble for leaking atomic secrets in 1945. DC Comics was raided by the FBI. So that amused me. These scientists as well, they're a bit mad. I mean, coming back to sort of element names and things like that, plutonium should be PL, but Glenn Seaborg thought the room stank, so he wanted to call it PU, stinky element, which was hilarious in 1940. Well, this is really bad. So the Germans, they don't like me talking about this, but I'm going to anyway. So they're based at a place called GSI Darmstadt. And it's actually in a town, a very small suburb called Wixhausen. Now, for your German speakers, that's already funny. Because Wixhausen, they wanted to call it Wixhausium, the element.
Okay.
That roughly translates in German youth slang as place I go to masturbate.
Okay.
Yeah, not a great element name. And part of the reason I got into sort of the naming as well is Lemmy from Motorhead is the most requested element name of all time. There was a petition.
What?
144,000 people wanted to name an element Lemmium because he just died as an element was discovered. And what better to represent a heavy metal than Lemmy?
Oh, how funny.
So there's all kinds of these weird stories there. And I mean, Alki also, he discovered one element by driving a Volkswagen Beetle as fast as he could up a hill. I mean, you can watch it on YouTube. It's bonkers. And so I just love this stuff. That's what I just focus on the stories. The other thing I'm really sort of passionate about, and I'm very keen to show that scientists are represented. And there's this preconception that we have that people who discover elements are sort of old white guys. And that is just not true. So one of the people I absolutely loved interviewing was Dawn Shaughnessy. She's discovered 5 elements. She's the most successful woman element discoverer of all time. She's a huge Star Wars nut. If you want to see her lab, send her a poster of Obi-Wan Kenobi. She'll let you through the doors.
I love it. Where is she located?
So she's at Lawrence Livermore, which is in Livermore, just outside San Francisco. And she's still working. She's still trying to discover elements. The Japanese, when they were trying to discover an element, it took them 9 years. They only discovered an element because of the Fukushima disaster. Skyrocketed energy prices around Japan. They were told to shut down all the experiments except one, and they insisted it be the one to discover an element, and kept going with it. They used to throw 113 coins in temples and pray to discover an element, because it was a sort of a matter of national prestige, which we have nihonium on the periodic table, which is named after Japan. There are so many very different stories, and every time I sort of found out more about somebody, I just wanted to know. So James Harris, for example, he was the first African American to discover an element, and I think most people probably aren't even aware of his name, which is an absolute. This is a guy who, when he came out of the army, he went to try and find a job as a chemist, and he was offered jobs as a janitor. He was once given an exam to sit for a chemist that was so simple, he said an elementary student could do it. He just picked up the paper, slid it across the desk, and said, I don't need a job that badly. And eventually he gets picked by Berkeley, and he's doing the separations, the purifications of the targets. That is the most complex chemical job there is in the team. So he was probably the best chemist in the team. And James Harris, eventually he's credited with 2 elements, 104 and 105. So this is a story that people aren't aware of, and I think it's important to be aware of those stories. Another one that really bothers me is Darlene Hoffman, because of the sheer sexism that she faced. So,
oh yes, tell me about this, please.
Yes, so Darlene Hoffman, she faced sexism at every single point. When she tried to become a chemist, her teacher took her away and said, "Do you really think that's a suitable profession for a woman?"
So what was the era here? Like how old?
So this was 1945. And she just turns around and goes, "Well, yes, I think it is," and takes on more work. Her father dies. She brings her mother and her sibling to live with her on campus, and she continues working while she's doing another job to fund her way through college. This is at Ames in Iowa State University. One guy, when her father died, gave her an exam on that day, on that spot, supposedly out of kindness, to allow her to go and do the funeral requests. I mean, they were just trying to push her out. When she gets clearance, they say that she can't possibly have clearance because she hasn't got a middle initial. They just make up this rule for her. So she says, "Fine, from now on, I want to be known as Xanthasia." So put an X in the middle of her initials. She wasn't going to let anything stop her. She gets to Los Alamos, which is a huge science complex. It's Los Alamos National, just outside Santa Fe in New Mexico, and she's going to take over the chemistry group there. And she arrives, and she's told immediately, no, you can't possibly do that. No woman works in chemistry. That's stupid. You go away now. And for 3 months, she is not allowed on site. And when she does get on site, her clearance to go and work on these bombs is mysteriously lost. She has to call in the FBI to get her clearance back. Now, while that was happening, the Einsteinium and fermium from the bomb came to the lab and was discovered. So she missed out on being a discoverer of 2 elements purely because of sexism.
I mean, her whole life.
That's the start of a story.
Yeah, like this is the experience of somebody who we have biographies on.
No, there is no biography of Darlene Hoffman.
Oh, really? So how do we know this?
So she wrote an autobiography, a sort of a very brief one. I've done some research. I've spoken to people that have met her. She's still alive as well. You can talk to her. She's in her 90s. But they go into machine shops, and she'd have Playboy pinups being stuck on the wall to try and intimidate her and things like that. Group because they thought she was a sweet little lady and things like that. It's atrocious what she went through. But she became a real advocate. The only reason we have people like Dawn Shaughnessy is because Darlene Hoffman absolutely spearheaded women in radiochemistry and said, no, people can do this work too. Anyone can do this work.
And this was in the 40s, right? You think back to 100, 200 years ago, how many women had a really important hand in this that we just don't know. It's just literally lost to history because men took credit or they worked with them and then never put their name on the paper.
She started in the 40s. When Dawn Shaughnessy joined her, that was in the mid-90s. So she was doing this for 50 years, advocating for women. And her story I mean, the terrible thing is that she actually takes over the Berkeley group, and they think they've discovered element 118. This was it's 1999. Huge celebrations. Obviously, she's finally got her element, and it turns out one of the researchers had faked the data.
Oh, that sucks. And she's
huge scandal, and so she loses out. And so Darlene Hoffman never discovered an element, but what she did do, which no one else did, she found the heaviest element on Earth that's ever been found. She found a sample of plutonium that exists from when the solar system formed. So there is an isotope of plutonium called plutonium-244. It has a half-life of, I think, 13 million years, and she found a tiny trace of it in the 1970s. And so that is the heaviest element we have ever found on Earth that has been naturally occurring that we haven't created.
That's very cool.
Yeah, she's badass. Cool. She's just badass.
Yeah. What percentage, though, I'm not expecting you to do like a big calculation right now, but if you were to look at all of the elements that had, maybe we should say, published names attached to them, all of the discoverers who got credit, I mean, it must be a tiny percentage that were women.
Yeah, it's a fraction. It gets much bigger, get to the modern era, when we actually have women who are recognized as chemists. It becomes much rarer. So from my knowledge, you've got Marie Curie, Ida Noddack, Irene Joliot-Curie, Marie Curie's daughter, Lise Meitner, and Lise Meitner was actually the person who discovered fission. She was actually Jewish. She'd fled Germany, and Otto Hahn, the guy who's often credited with the guy who won the Nobel Prize, actually wrote to her and said, "I've got this weird result. Can you explain it?" And she went, "Yeah, the elements, obviously." And she gets left out for the Nobel Prize.
Of course. Oh my God.
But she does have an element named after her now, because the German group was so bothered by this, they named an element after her. And she is the only woman with an element named solely after her.
Good.
Curium is named after Marie and Pierre Curie. Meitnerium is solely after Lise Meitner. Anyway, so you have those women who were doing work in the 1930s typically. And then you have Perko Escala. She was part of the American group in the 1970s. You have Nancy Stoyer, Dawn Shaughnessy, the modern era. And you have people who worked at Oak Ridge in purification of the targets. And that includes someone called Clarice Phelps, who is the first African-American woman that I'm aware of to discover an element. You also have Alonso, who was the first. Cara Alonso was amazing. She sort of did a bit of spy work on a Mississippi boat, one of those sort of paddle steamers going down the things to try and sneak the element out of the Russians. And that was element 106, because the Americans and the Russians were both trying to claim that one, and so she's credited with element 106. So that's another name for you.
Jeez, I mean, again, like, you could, for the rest of your life, if you so wanted to, write a book about every single element. Like, there's so many stories about every single element. I have to know, like, what was your process like? I know you focused on story and on the real human story, but I imagine like a beautiful mind style grid on your wall where you're just culling and culling and culling to decide what to actually put into the book.
No, there was a beautiful dent in my wall where I was smashing my head against it, going, "Oh my God, what am I doing? Why did they do this?" I was just trying to wrap my head around. I'm not a nuclear physicist. I'm not that bright to do this kind of stuff. So I just kind of the key thing was to go around the labs and actually to meet the people and to talk to them. Because what I wanted to do was to make sure that any information in there was accurate and from the experts. And so I sort of framed it around that. One of the narrative things I thought about framing it around was, rather than doing the elements in order, do a little bit of the history and certainly tell the historical story, but actually frame the story almost like a travelogue. So first of all, I went to the Trinity test, which is the first place they detonated an atomic weapon. Then I went over to Oak Ridge in Tennessee. I went to Livermore and to Berkeley in California. I went over to Dubna and met Yuri Oganesyan, the only good person alive who has an element named after them. I went over to Japan, which was amazing, and followed this. They've actually engraved a periodic table from the train station in Waco all the way to Riken, where they discovered the element. And so I followed this sort of yellow brick road, if you like, of periodic table elements right up to their doorstep. I went over to Australia to see how they're trying to perfect the beam so they can discover new ones. I went over to Germany and walked the full length of 108 meters, which is the length of a particle accelerator that you need to shoot it at about 20% the speed of light. went over and I tried to break into Enrico Fermi's house, the Italian military, which was a bit. It turns out it's now kind of yeah. Let's not go into that. So there is a lab that shall remain nameless, but I think I might have just said where it is. And they have a very unique process. So to purify your plutonium, and sorry, to isolate it, you need to shake things. And the problem is you're dealing with radioactive material. So these things are typically done in very protective conditions. You've got little lead-lined bricks. In Oak Ridge, they actually have something called hot labs. They've got these. You've seen Minority Report, where he does the balletic flicks.
Yes.
Combine that with the power loader from Aliens, and that's kind of what they use to sort of puppeteer the material because it's highly radioactive. Anyway,
all right.
This lab's got the bricks, and they need to somehow shake their sample of plutonium. How do you do it? They need something that's easy to clean because obviously they want to recover anything. Even a bead is worth 10 times their salary. They need something that's easily washable. They need something that they can replace, and they can't find any part that fits the bill until one of them, again, who shall remain nameless, says, "Well, why don't we use an anal vibrator?" And so they pop down to the red light district and they buy an anal vibrator. You can adjust the speed on it. Fantastic. And they stick it in there and it shakes up their sample. It works a treat. Fantastic. Now they've got to justify the expense claims. Now, it gets a bit awkward. The problem, though, is that it breaks. First one breaks really quickly. And they can't put through a second claim for an anal vibrator.
No, this is the time when you just pay cash. Come on, guys.
Well, they're a bit tight. So they send down one of their grad students with his broken anal vibrator into the red light district, into the sex shop, puts it on the counter, says, "I'm really sorry, but after 45 minutes of continuous use, my vibrator is broken. Can I have a new one, please?" And to this day, that's what they use in the lab.
Amazing.
Not entirely sure I should have told that story, but there we go.
That's how we should have opened this episode. That's incredible. Oh my gosh. I mean, I could keep talking to you for hours and hours and hours. We've already been talking for an entire hour, Kit, and I would be like, I'd feel really guilty if I just kept going. But there's a couple more things that I would love to know from you before we wrap up for the day. I always close my episodes by asking my guests the same two questions, and I want to get to those closing questions in just a second. But we didn't spend that much time talking about kind of your process and your journey. I mean, we talked a bit about your maybe philosophy or the way that you write, but you yourself have a chemistry background, right? Actually, a pharmacy background. Before you became a science journalist, you actually worked in this field. What kind of how long were you doing that, and what made you switch over to writing?
So I went in to do a master's in pharmacy, which is the qualification you have in the UK. I think it's a doctor in the US, but I was doing 5 years basically, and I worked 6 months in a hospital, 6 months in we call it Tesco. It's like our version of Walmart, if you imagine that. Basically doing prescriptions, and I learned something very, very quickly, which is that I hate sick people. No, I'm joking. My problem was that I was learning all these clinical skills. I was learning sort of diagnosis, treatment, what all these drugs did. But I wasn't using any of that. I was literally just taking a piece of paper and I was trying to find a box and making sure the label was correct and giving it out to somebody. And there was no fun in that. And so I looked for alternatives. When I graduated, I tried to find a job sort of doing anything, really. I almost went into the Navy. But in the end, I found a job working as a copy editor on a medical journal. From there, I became a reporter. Managed to get a few good stories and just sort of took off from there. And I realized that actually writing is about as much fun as I can possibly have. I love it. I love learning new things. And I love being the person that tells people new things that they don't know. So I just took off from there.
I love that. Yeah. I mean, I'm finally going back for my PhD now, but I feel like I resonate with that because working as a science communicator, doing interviews, I don't write as much. I actually quite hate writing, but telling stories, I do a lot of it on camera and in podcasting. I feel like it's like the best job in the world because I get to just learn new stuff every day.
Exactly. I mean, that was the one thing I loved about Chemistry World is that every day I was going in and I was finding out something entirely new. And I've actually left chemistry world now. I'm sort of writing full time and sort of focusing on one issue and being able to sort of sit with people. I kind of want to be sort of the chemistry version of Louis Theroux, if that makes sense to you, sort of the documentary maker where he goes and finds these weird stories and explores them in depth. Because the more you dig into a story, the stranger the rabbit hole goes. I just become fascinated. I'm the kind of person that gets lost on a Wikipedia page, just clicking and clicking and clicking. And
Oh, yeah. You could spend days on Wikipedia just going deeper
yeah,
and deeper. It's amazing.
last night I was learning about the do you know about the government story about the radiation cats?
No.
Here's a thought experiment that anyone can do at home. You've got a pile of radioactive waste. That's going to last about 14 million years. It's going to last 3 times longer than human history, which is 10,000 years, say. How do you tell someone 10,000 years in the future that there is radioactive waste buried there?
Yes, I did. I did a story for like the Travel Channel or something like that on this place called Whip, where I went to. What do you call it? Whip. Whip is I can't remember what it stands for, but it's a Permian salt mine where they're burying basically all of the stuff from nuclear testing during the Cold War, and they don't know. Like it's just gonna the mine creeps, right? Like the salt naturally kind of closes in on itself. And that's the big question is do we put a flag over it? Like, is there some sort of plaque? And what language do you write it in? Like, I don't know. Is it pictures like on the golden record in Voyager? Like, I have no idea.
Exactly. It gets even. I mean, they actually are science fiction writers. You know, how do you do this? And one guy suggested starting a fake religion that worshipped radioactive waste and passing down the books of the locations and things like that. Another person said breeding cats because cats hang around with humans, but they have no discernible purpose. And why not sort of breed cats that can change color when they're near radiation? And so there's all kinds of, I mean, so this is just a rabbit hole I went down last night. It's just fascinating. It was called the Human Interference Task Force, if anyone wants to have it on Wikipedia.
Okay, so when that book comes out, you're coming back on this show for sure. Oh my gosh. So Kit, so I always ask my guests the same 2 questions to close out the show, and they're really, really big picture questions. So I want you to think about the future, which I'm assuming you do in your work. And I want you to think about it in whatever context is relevant to you right now as you sit here talking to me today. So this could be the future of humanity. It could be the future of the cosmos. It could be the future of your next book. It could be anything. Number one, I want you to tell me, what is the thing that keeps you up the most at night? The thing that you've been really focused on, struggling with, maybe you're a bit pessimistic, even cynical about, things aren't looking good. And on the flip side of that, what are you genuinely optimistic about? What are you looking forward to in a real way?
Okay, the optimism question is probably the easier one. So I'm going to start with the optimism. Actually, no, let's do the negative one, then we'll go to the optimism. That's much better. The answer is things like Brexit and some of the stuff that's going on at the moment. I think we've got to a point where a lot of hatred that has been sort of stewing for a long time is starting to bubble out in society, and it's really not a nice place. And I'm very worried about what that's going to do in the short term. I think in the long term, actually, we're going to be able to sort this out. I think there are more good people than bad people. But we have a very nasty culture at the moment in certain circles. We're too fast to shut people down. We're too fast not to listen. And I am deeply concerned with where things are going, particularly sort of politically, as I mentioned, Brexit, but also certain things in America. When we're recording this, there's been some utter tragedies recently. I'm really worried about that. So that's the kind of stuff that actually bothers me because I don't have any kids, but my brother's got a whole gaggle. He's got 5, and I do worry a little bit about what sort of world they're going to grow up into. But optimism aside, I did a talk at Imperial College in London earlier this week, and the questions I got from the 16-year-olds were some of the smartest questions that I have ever been asked by anybody. They were just so switched on. They know exactly what's going on. They know exactly what's happening. I have absolute confidence and faith in the next generation. I have an absolute faith in young people. I think we don't give young people enough credit, and I think that we're going to be okay because if we can somehow sort out the next couple of years, which is going to be a bit rocky, and sort of certainly whole climate change, things like that. I think actually the people that are coming through, the young people, are very, very bright. I think we've got an exciting future.
Yeah, and I think that like if we were to look for a silver lining at all, with some of the political, issues that we've been dealing with and the social issues that we've been dealing with, it's that they are so severe and so obvious. Oftentimes we talk about this, that like we have been making so much progress, right? Historically, when you look at the timeline, we're bending in a progressive way. And so sometimes, you look at Brexit, you look at Trump, you look at the mass shootings that we've been dealing with, all of these things. And it's so hard to not.
Yeah, I keep forgetting he's not Voldemort. Do we just say his name?
Yeah, I know. Yeah. Oh God. Yeah. But the reason that it's such a punch in the gut is because we're in a different place now. Like Trump 150 years ago wouldn't have surprised anybody, I don't think. But Trump now feels like a punch in the gut because we have made so much progress. And so I think that's one of the great things, like you said, about kind of the quote unquote, I mean, it makes us sound so old, the young generation, but it's that they're like, no, I'm not standing for this. I'm not going to live in that world. And I think that's important.
Yeah, 10 years ago, if you had told me that the gay marriage would be legal in the United States, I'd have laughed at you. I would not have believed it. And here we are, which is just fantastic. So I think there is so much progress that is happening. You're right, but we shouldn't sort of let the noise attract, but at the same time, we shouldn't ignore it. I think we have to be aware of the threats and the dangers.
Agreed. Well, gosh, Kit Chapman, the book is so good. I completely agree. The book is Superheavy, Making and Breaking the Periodic Table. Kit, thank you so much for joining me today. This was a fascinating and surprisingly really, really funny conversation.
Well, thank you for having me. I'm sorry I diverted into so many different little rabbit holes, but that's just how my mind goes. So,
never apologize. It's what I love about doing this show. It's so much fun. And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.